Assalamualaikum and hi everyone. So, this is another video on chapter 3 electrochemistry. We are still in subtopic 1 galvanic cell, and in this video you will be able to define standard reduction potential or electrode potential and then standard cell potential E0 cell. Draw and explain standard hydrogen electrode She, construct standard reduction or electrode potential series by using She, and also use standard reduction or electrode potential values to compare the relative strength of oxidizing or reducing agents, calculate standard cell potential E0 cell, and also predict the spontaneity of a redox reaction. So now, let's start with the first one. We're going to look on the E0 half cell versus the E0 cell. So what are the difference between these two? The first one, we're going to look on the standard electrode potential, or we could also call it as the E0 half cell. So please make sure you read this carefully and then look at the label over here. Okay. You have E0 again. Why do we have not over here? Because it is standard electrode potential. Okay, when we talk about electrode, meaning only one electrode of one half cell. Sometimes we also call it as electrode potential, but there is some difference between electrode potential and standard electrode potential. So the difference is, okay, over here, okay, if we have standard electrode potential, meaning it is at standard state. This one is actually already been discussed on the previous video. So this is just a refreshment for you guys. Okay, so just to refresh back your memory, so E0 half cell is a measure of the ability of a half cell to attract electrons towards itself at standard state, or we also call it as the ability of one half cell to undergo reduction process. Okay, so the magnitude of the electrode potential depends on the tendency of the metal or non-metal to lose electron to undergo reduction process. And then I already mentioned to you about the E0 half cell. We have it either E0 anode or E0 cathode. The name just refers to if the electrode is an anode, so we call it as E0 anode. If the electrode is cathode, we call it as E0 cathode. So that's just the difference. The value of the E0 half cell, like I mentioned before, we will take the value from the standard reduction potential table. Okay, now the next one. We're going to discuss on standard cell potential. So for standard cell potential, we label it as E0 cell. So what's the difference between E0 half cell and E0 cell? Okay, the name itself shows you the difference. So for the half cell, if you can recall back your galvanic cell or your voltaic cell, okay, let me scribble a bit. Your cells, what we will have, okay, the structure. So we have voltmeter over here, and then you will have in your circuit two different electrodes, okay, inside two different beakers, and then here you will have your salt bridge, and then inside each beaker we will have electrolyte, okay, and then two electrodes. So this is half cell. Okay, let me just circle it for you. Okay, this is half cell. Okay, so our half cell over here will have the value of E0 half cell or the E0 electrode. So for the E0 cell, it corresponds to the whole cell over here. Where do we get this value of E0 cell? The value of E0 cell is over here, the one that you will read from the voltmeter. So this is the value of E0 cell. Okay, so what does this E0 cell shows? So it shows the difference in electrical potential of electrode measured at specified temperature, usually 298 Kelvin, meaning 25 degrees Celsius, with all components in their standard states. Okay, what does it mean by here? Each half cell has their own value, and the difference between the two half cells will be recorded over here. Okay, let's say the first half cell is negative 2.5. The second half cell is negative 1.1 volt. So the difference between the two half cells will be recorded in the voltmeter. Okay, and please take note that besides the name E0 cell, it is also known as voltage or the electromotive force. Okay, not the E0 cell. I mean the difference here, the difference in electrical potential, the standard cell potential, sometimes is also called as voltage or electromotive force, EMF. Okay, so if the question talks about the EMF value, so what does it mean? The question wants you to find what is the value of the E0 cell. So the SI unit, the standard unit for the cell potential or the E0 cell is volt. 1 volt equals to 1 joule per coulomb. So coulomb is the SI unit for electrical charge. So since we are using voltmeter over here, we are currently trying to find what is the volt. Okay, the electrical difference, the electrical potential difference between the two half cell. Okay, so it is measured by a voltmeter. Okay, now standard cell potential. We're going to discuss more on this standard cell potential, the E0 cell. Okay, please take note that I'm reading it as standard cell potential. Why I keep on repeating this? Because later on 3.2, okay, we will have a question that will use only E cell. There will be difference between E0 cell and E cell. But for now, let's discuss for this one. Okay, the standard cell potential. How to calculate the standard cell potential? Calculating standard cell potential, we will use this one equation, which is E0 cell equals to E0 cathode minus E0 anode. Like from the definition itself, just now, the E0 cell states that it's a difference in electrical potential of the electrodes. So what are our electrodes? We have cathode and we have anode. So to calculate the difference, it must be E0 cathode minus E0 anode. Again, where are we going to find the values of E0? We're going to take it from the standard reduction potential table. So let's take a look on some example calculation on the E0 cell, a very simple calculation. So example 1, calculate the standard cell potential for the following reaction. So the reaction that I have is zinc solid plus copper 2 plus aqueous to produce zinc 2 plus aqueous plus copper. Okay, so by experiment, we can directly measure what is the value of the standard cell potential. So if it's talk about the standard cell potential over here, standard cell potential. So what does it mean? Okay, it means it asks about the value of the E0 cell. Okay, so if we have a setup of our galvanic cell, okay, we can see over here, you can see over here that you have two different beakers with two different electrolytes and two different electrodes. Okay, And then at the voltmeter, there is a reading of 1.10, positive 1.10. So this is the value of the E0 cell. This one, if we have an experiment set up like this in the lab. Okay, but how are we going to determine what is the E0 cell if we don't have a voltmeter? How are we going to calculate? Okay, so from the question, you are given zinc solid plus copper 2 plus aqueous to produce zinc 2 plus aqueous and copper solid. So what you need to do from the equation is find which half equation belongs to anode and which half equation belongs to cathode. Okay, so let's do this in the next slide. Okay, from the question just now, so let's determine which is the oxidation and which is the reduction process that occur at our anode and our cathode. Okay, so first match the species, so zinc with zinc. Okay, and then we have our copper 2 plus with copper. So if you look over here, zinc towards zinc 2 plus. Okay, so like we did from the previous semester, if we are not sure either it is oxidation or reduction, try to balance the equation first. Okay, so let us balance it over here. Okay, so let's use a black color ink. So I have zinc solid to become zinc 2 plus aqueous. So to balance this equation, we will add 2 electrons over here. So we know if the electrons are on the right hand side, on the product side, meaning what do we have here? We have an oxidation reaction. So where does the oxidation reaction occurs? It occurs at anode. So for electrochemistry, when talking about either electrolytic cell or inside the galvanic cell that we are discussing right now, the half equation, we will label it based on its electrode, meaning either it is cathode or anode. So since this is an oxidation process, okay, so let me just write it down. Okay, so oxidation. Okay, where does oxidation occurs? Oxidation will occurs at anode. So you label as anode. Anode is compulsory and better if you can put over here as oxidation. So automatically we know that at cathode, okay, what is the process that occurs at our cathode? It is reduction. So reduction process, what is the equation? So the equation will be copper 2 plus aqueous plus 2 electrons to produce copper solid. Okay, so this will be our equation, the half equations. Okay, anode, cathode. Okay, so right now we are trying to find what is the E0 cell. Okay, we want to know how do we get this value. So from the equation, we know the equation that you're going to use is E0 cell. Okay, E0 cell equals to E0 cathode minus E0 anode. So this will be the equation. Okay, you need to find what is the value of the E0 cell over here and then the E0 half cell over here. The E0 half cell for the cathode and the E0 half cell for the anode. So where are we going to get this value? So this value is either given to you in the question in exam or you need to find the value from the SRP table. Okay, if you get the value directly from the SRP table, you need to make sure you look on the reduction equation. So for cathode, okay, it is already a reduction equation. So from the SRP table, find copper 2 plus 2 electron to produce copper. So the value here, okay, let me write down, is copper 2 plus, okay, subscript down here to become copper, and the value is positive 0.34 volt. Okay, and then for the anode, for the zinc over here, the process that you write down over here is an oxidation process, but the value, the E0 half cell over here, it must be a standard reduction value. So if you look on the SRP table, okay, the equation that you need to find to get this value is zinc 2 plus aqueous plus 2 electron to produce zinc solid. Okay, so the value over here will be for zinc 2 plus to produce zinc, and it will be negative 0.76 volt. Okay, some of you might wonder, since the equation is reversed over here, must we reverse the sign over here? No, you don't have to. Okay, this is a totally different thing when from the one that you have learned in chapter 2. Okay, here, why we don't have to reverse the value? Because in the equation, it is E0 value. So the E0 value, like I mentioned before, the E0 half cell over here, what does it represent? Okay, so the value over here, it represents standard reduction. Okay, so if I can write it down over here, it's your standard reduction value. Okay, so what happens if you reverse the equation? If you reverse the value over here, if you put it as positive 0.76, it becomes an oxidation value. So if you have an oxidation value, it is not valid in this equation. So to make it simple, don't change anything, don't change any value over here, and you will not times it by 2 or divide it by 2, you will do nothing. You will just use the value as it is. Okay, so from that, so let me just label this. So since this is our anode, so it will be our E0 anode. The value of E0 anode is negative 0.76 volt, and the value of our E0 cathode over here, okay, is positive 0.34. Once you have determined these two values, so you can straight away substitute inside the equation. So it will be positive 0.34 minus negative 0.76, and we will get the value as positive 1.10 volt. Okay, so this is how you calculate the standard cell potential from calculation. Okay, and the value will be the same with the one that we have recorded in the voltmeter. Okay, again, you will get this positive 1.1 value when the concentration inside here is 1 molar. The concentration inside here is also in 1 molar. In other words, it must be at standard condition. Okay, so this is the first example. So now let's move on to the second example. So this is example 2. A voltaic cell houses the reaction between aqueous bromine and zinc metal. So this is the equation given to you, and as you can see from this equation, so Br2 aqueous plus zinc solid to produce zinc 2 plus aqueous plus 2Br minus aqueous, and given to you the value of the E naught cell, meaning the overall cell potential, the standard cell potential is positive 1.83 volt. So the question, calculate E naught bromine if E naught zinc is negative 0.76. So again, how are you going to tackle this question? Okay. Is it necessary for you to write down the half equation? No, it's not necessary for you to write down the half equation, but you need to know which equation, which reaction occurs at anode and which reaction occurs at cathode. So identify what is the oxidation reaction and what is the reduction reaction. Okay, so as easy as you can write this down, okay, just label it. Okay, Br2 over here. So Br2, it will be with Br minus, zinc will be with zinc 2 plus. So the easiest over here, you can see zinc from 0 oxidation number to positive 2, meaning you will have an oxidation reaction over here. So this is oxidation. So where does oxidation occurs? Oxidation occurs at anode. Okay, once you know oxidation occurs at anode, okay, what does it mean? Okay, meaning over here, the E naught zinc, you can put it as E naught anode. So automatically, the E naught bromine over here, okay, E naught bromine is at your cathode. Okay, at your cathode where the reduction process occur. Okay, so this is, you label it as E naught cathode. Okay, why determining which one is anode and which one is cathode is important? This is because the one that you will write down inside your equation, it will be, okay, E naught cell equals to, okay, let me just write down the answers over here. E naught cell equals to E naught cathode minus E naught anode. Okay, cathode, E naught anode. Once you have determined which one is anode, which one is cathode, so the calculation will be easy for you. So substitute all the values that we have. So over here, let me just write it down back. Okay, since we have a specific anode and cathode over here, so our cathode is E naught bromine. Okay, can you write it like this, E naught bromine, instead of the process, which is Br2 to Br minus, meaning E naught Br2 Br minus. If the question already give you like this, E naught bromine, so you can write it down like this. But if the question doesn't mention anything, okay, you can write down like this, the process. But if, let's say, you are unsure on writing it down, how to write down this part over here, so it is allowable for you to write down just like this, E naught bromine. Okay, so let's continue. So minus over here, your E naught zinc. Okay, because that is your cathode. So substitute all the values that you have. E naught cell is positive 1.83 volt. Again, make sure at the final answer you must put your unit. So the one that we want to find is E naught bromine. So write it down back. Please do not leave it as E naught cathode anymore. Okay, put specifically as what the question asks. What does the question ask? E naught bromine. Okay, so write down what does it ask for. Okay, minus the value of E naught zinc is negative 0.76. So make sure you put your mathematical knowledge in use. write down the equation correctly. Okay, because your chemistry part is only up until here. E naught cell equals to E naught bromine minus E naught zinc. The rest of it is your mathematical knowledge. Okay, so rearrange equation. E naught bromine equals to positive. Please make sure you write down the sign. If it's positive, put as positive. If it's negative, put as negative. Positive 1.07 volts. Okay, please do not forget the unit. It must be in volt. Capital V. Okay, why it is important for you to write down either it is positive or negative? Because this value later will show you something else. Okay, we show you either the reaction is spontaneous or non-spontaneous. Okay, the next part, we're going to discuss on standard hydrogen potential She. What is this? So, how does the standard electrode potential, the E naught half cell values are measured? Okay, up until now, what I have taught you is how to use the value inside the SRP table. So the value on the SRP table is the value for the standard electrode potential, the ability for the half cell to undergo reduction. Okay, but how do we measure the value actually? How do we came up with the value? So, to get a value of E naught something, E naught, okay, to get this value, okay, to get the value over here, the E naught value over here, it must be done in a full electrolytic cell. Again, when I said full galvanic cell, when I talk about full galvanic cell, it must be the full setup. Okay, what is your full setup? So you must have, again, your voltmeter. Okay, I've been teaching you how to draw the galvanic cell, so make sure you know how to draw it correctly. Okay, the salt bridge. Okay, it must be a complete cell like this. Okay, but the value that we want to find is only the half cell. Can we only measure the half cell? Meaning, you just put one half cell over here and then voltmeter. Okay, and the voltmeter will show you the reading. Can it happen like that? No. Why? As you can see from the drawing itself, it is not complete. When you don't have a complete circuit, meaning we cannot know exactly, we will not know exactly what is the value of electron flow. So thus, we cannot determine what is the volt that we're going to get. So how are we going to measure this? Okay, so example over here, I gave you. So example, zinc and copper 2+. So this is our half cell over here. So it is impossible to measure the absolute value of an electrode potential directly. Okay, what does it mean over here? It means this one. We cannot measure directly what is the value of this half cell. Okay, so the standard hydrogen electrode She is used as a standard reference to measure the electrode potential of the other half cells. And the standard hydrogen electrode E naught She, we give it the value of 0.00 volt. So your SRP table is constructed by having example one half cell over here and then connected, okay, to She over here. So we will have one setup for She over here and then connected by a salt bridge. Okay, so how does this She looks like? Okay, so let me erase this first. Okay, for me to show you how does the standard hydrogen electrode looks like. Okay, so this is the setup for your standard hydrogen electrode, where we will have over here a platinum electrode immersed in 1 molar of aqueous solution of a strong acid that we will label as H plus aqueous 1 molar, which through which hydrogen gas at 1 atm is bubbled. So the setup compulsory, it must be like this. So this is our shape. Platinum electrode, okay, your inert electrode, okay, and then the electrolyte compulsory, it must be H plus aqueous 1 molar. Where does it come from? A strong acid. And we will bubble H2 gas at 1 atm pressure. Okay, so how will you draw this? Okay, so if you were to draw your She, you can simply just draw it like this. So I hope you can see down here. Okay, just draw one test tube like this, okay, with an outlet over here, and then your wire, okay, your platinum inside a beaker. Okay, so you will label this H plus aqueous 1 molar, and then this is your PT platinum solid, and in the outlet over here you will put as H2 gas. It must be 1 atm pressure. So when labeling your galvanic cell, please make sure you label completely solid. Okay, it will be just solid. But for gas and for also aqueous solution, it must has its concentration. For the gas, it must have its pressure. Okay, so this is how you draw your standard hydrogen potential She. Okay, how are we going to use She inside our galvanic cell? So let's take a look on a few examples. Okay, our standard hydrogen electrode, it can either be cathode or at the same time it can be an anode. Depends on what if the other half cell. Okay, so we're going to discuss first She as cathode. Okay, determination of the standard reduction potential of zinc metal. So this is the setup when we use She as cathode. We have our half cell over here, zinc, okay, the electrode zinc immersed in zinc sulfate solution, okay, 1 molar, so it must be at standard condition. Okay, and then we have our She over here, where we have a test tube, okay, with hydrogen gas inserted. Okay, and then the electrode used is platinum electrode, our inner electrode, immersed in a strong acid. Okay, so strong acid 1 molar, which we will have our H plus positive. And then if we do this setup, the value of the E naught cell will be positive 0.76. Okay, so here we will get the standard electrode potential of She is 0.00. This is a standard value. We put it as 0 as a reference. Okay, as a reference for us to get what is the value of the other half cell. Okay, so now let's look at the calculation on how are we going to find what is the value actually over here. So bear in mind, this is not the value of the half cell over here. It's the value for the overall reaction. Okay, so from this setup, you will have the cell potential. It will be like this. So this is a revision on your cell potential. So on your anode over here, so let me just label. Okay, here is your anode. Your anode will be your negative terminal, and over here is your cathode. So your cathode over here will be your positive terminal. Okay, now just a revision on how to write down your cell potential. So at your anode, okay, the electrode is zinc. So remember the cell potential, the left hand side, it must be anode. And remember our ABC. So A, B, C, anode. Okay, and then in the middle we have our bridge, which is the salt bridge on, and on the left, on the right hand side, here is our cathode C. Okay, so zinc. Okay, we have the line over here to show that it is different phase. Zinc 2 plus aqueous 1 molar. You must write it down full like this. The salt bridge, and here the process that will occur at your She over here is H plus to produce H2 gas, and then the electrode is your platinum electrode. Okay, so now let's take a look on the full equation. So calculating standard reduction potential of zinc. So this is the the cell potential that I give to you. Sorry, the cell notation. I keep on giving you this wrong term. Okay, so I write it down over here. This is your cell notation. Okay, and from this cell notation, over here is our anode, and over here is our cathode. So the process, it shows the process. So at anode, the process is oxidation of zinc towards zinc 2 plus. And then at the cathode, a reduction process. Reduction from H plus to H2 gas over here. Okay. And as you can see, H plus aqueous 1 molar, and we have a phase barrier over here, H2 gas 1 atm. You must write down the pressure, compulsory. And then we must complete our cell notation with platinum solid over here. Okay. Again, why are we using platinum solid over here? Because the medium that we have in our She, we don't have any active electrode. So that's why we are using an inert electrode. You must have an electrode. So at the end of this cell notation, on the left end and also at the right end, you must have solid electrode. Okay, so the half cell equation at anode oxidation. So this is the equation. And then at cathode, this will be your equation. H plus electron to produce H2. So balance 2 electron plus 2 H plus. So you will get the overall equation like this. Okay, cancel out the electron and you will get the overall equation. So we already have the value of the E naught cell, and we have the value of She is 0. Okay, so let me just write it down over here. So E naught She, or sometimes, okay, so it is 0.00 volt, or sometimes it is write down as E naught H plus 2 H2, just to show the reduction process is 0.00 volt. And then from the voltmeter, we already have the value of E naught cell. So substitute inside the value. So meaning over here, our She is our E naught cathode. And the one that we want to find, the E naught anode, is over here. Okay. E naught anode is equals to E naught zinc that we want to find. So by using E naught cell equals to E naught cathode minus E naught anode, okay, substitute all the values that we have. So this is the E naught cathode and this is the E naught anode. So a proper way of writing it substitute the value, and you will have the E naught for zinc, the standard reduction potential for zinc 2 plus towards zinc is negative 0.76, and if you compare this value to the value inside the SRP table, you will get as negative 0.76. So that's why we will not simply just take whatever value in the voltmeter. Okay, you need to find the value of the half cell by using this equation. Okay, so this is the first example. So let's take a look on the second example. The second example is our She as anode, meaning it will undergo oxidation process. Okay, so determination of standard reduction potential of copper metal. So this is our setup. Okay, we put our She at the left hand side, which is for the anode. Okay, the setup is still the same: H2 gas, platinum electrode, inner electrode, and 1 molar HCl. You have your salt bridge over here, and then at the other half cell we have our copper solid electrode immersed in 1 molar copper sulfate solution, our electrolyte. Okay, and when we do this setup, the reading that we get from the voltmeter is positive 0.34 volt. Okay, now maybe by now some of you wonder, how do we know the She will be an anode or will be a cathode? Okay, the clue here is on the value of the voltmeter. If you are able to do the experiment in the lab, you will see. Okay, what do I mean by this? When you construct this set for the galvanic cell over here, okay, when you do it one by one, okay, the value of the voltmeter, if you get the correct circuit, okay, if you construct a correct galvanic cell over here, the value of the voltmeter will show you a positive value, meaning you will have a spontaneous reaction. Okay, what does it mean when you have a positive value? Your anode and your cathode is correct. But if, let's say, when you construct the galvanic cell and the value on the voltmeter give you a negative value, so what does it mean? Negative value meaning the needle over here, it goes to the left. So it means that your half cell is wrong. It needs to be the other way around. In other words, half cell awak terbalik. So kena betulkan. Okay, so that's why, that's how we determine either it will be a half cell will be anode or cathode. Same goes as She. How do I know my She over here is anode? Okay, by experiment. Okay, when I set up the galvanic cell over here, if I put it as anode, I will get a positive value. But if, let's say, the She is at cathode, the copper half cell is at anode, I will get a negative value. Okay, but for now, just understand that this is your setting. Okay, so the value of our She is still 0.00 volt, and the value of the E naught cell over here, meaning the cell potential, the difference between the two half cell, is positive 0.34. So again, let me remind you, this is not the value directly for copper half cell over here. Okay, so as if I can write down, so over here, since this is your anode, okay, so this is anode and this is cathode, so you will get the value of E naught anode over here, and this is the value of E naught cathode. So our E naught anode is our E H plus H2. Okay, is the value of She, which is 0.00 volts, and the E naught cathode is E naught copper to plus reduction of copper to plus towards copper. So this is the value that we want to find. So given to you here the cell notation. So if you can see the cell notation over here, okay, platinum solid and then H2 and H plus is the process. Okay, process of hydrogen gas oxidized to H plus. Why it is oxidized? Because it's at anode, an oxidation process. And then the salt bridge on the cathode, copper to plus to become copper, a reduction process. So now let's take a look on how to do the calculation. Okay, so calculating standard reduction potential of copper. So this is the equation. Okay, to find the overall equation. So I will not discuss about this because it is the same. Okay, cathode, anode. So for oxidation, okay, it will be hydrogen gas to H plus. If reduction, H plus to hydrogen gas. It's just the other way around. Okay, so like we have stated before, this is our anode, and this is our anode cathode. Okay, our anode cathode is anode Cu2 plus Cu. Our anode is anode H plus H2. Okay, so put all the values inside our equation. E naught cell equals to E naught cathode minus E naught anode. Okay, and you will get the value for the reduction, standard reduction potential for the copper half cell will be positive 0.34. And do compare it inside your table. You will get the same value. Okay, so this is just the overview on how the values on the standard reduction potential is constructed. Now, we're going to proceed with another part of 3.1. Okay, the relative strength of oxidizing agent and reducing agent. So I hope you still remember what is an oxidizing agent and what is a reducing agent. Okay, so just a quick recap. So if it is an oxidizing agent, so let me write down here, oxidizing agent. Okay, that particular species will undergo, okay, what process? It will undergo reduction process. So the species that undergo reduction, we call it as the oxidizing agent, and reducing agent will be our the one that undergo oxidation process. So let me just write down over here. So our reducing agent is that one species that will undergo oxidation. Okay, so this is just a quick recap for you. So the one that we're going to look now is the strength of the oxidizing agent and the reducing agent. We want to look which species is a better oxidizing agent, okay, and which species is better reducing agent, and vice versa. And where do we get this value? We will get this value based on the SRP table. Okay, so the SRP table is very, very, very important in electrochemistry. Okay, now refer to the list of standard reduction potential, our SRP tables. Okay, so the oxidizing agent will be on the left hand side of the half cell equation, and the reducing agent will be on the right hand side. Okay, why is this so? Okay, so example, so this is some values that I take from your standard reduction potential, and please bear in mind, from the SRP table, the equations that we will have is a reduction process. Okay, so when you have a reduction process, what does it mean? by the oxidizing agent on the left hand side. Since this is a reduction process, okay, the species that undergo reduction is nickel, copper 2 plus, and silver plus ion. Okay, Ag plus ion. Okay, so let me just scribble here. Okay, oxidizing agent. Okay, undergo reduction. Okay, so that's why on the left hand side over here, this is our oxidizing agent. Okay, you must know precisely which one is oxidizing agent, which one is reducing agent. Okay, if you take directly from the SRP table, it will be on the left hand side. Okay, and on the right hand side, the reducing agent. Okay, this is our reducing agent. So the reducing agent, what reaction will it undergo? It will undergo oxidation. Okay, so it's actually the reverse equation. So it will be, okay, let's say I take nickel. So nickel solid to produce Ni2 plus aqueous plus 2 electrons. So like I mentioned before, reducing agent will undergo oxidation process itself. So from this equation, okay, which species undergo oxidation? It's nickel over here. So that's why we label nickel as the reducing agent, not nickel 2 plus. Okay, if you read straight away from the SRP table like this, the left hand side will be the oxidizing agent and on the right hand side is the reducing agent. But if you are reading from a half equation, okay, what do I mean by this? Let's say this is equation at anode, okay, and then you have another equation at cathode. So let's say I have copper 2 plus aqueous plus 2 electron to produce Cu solid. If you are taking the information from the half cell like this, the oxidizing agent and the reducing agent will be on the the left hand side. Okay, it's just that since this is oxidation, so this is a reducing agent because it is used to make sure that copper 2 plus undergo reduction. Okay, so cathode reduction. So copper 2 plus is called as the oxidizing agent. Why? Because it is to ensure that the nickel over here will undergo oxidation. Okay, so the next part, okay, that we want to discuss the strength. Okay, how do we determine which one is a better oxidizing agent and which one is a better reducing agent? So we're going to discuss by looking at the value over here. Okay, so from this value, I need you to correct your arrow inside your notes. So follow the arrow that I have in this video. Okay, so going down over here, the more positive or bigger the value of the E naught, the stronger the oxidizing agent. Okay, so we're going to refer at the value of the E naught over here. So negative 0.25, positive 0.34 and positive 0.80. So like I mentioned before, this is a standard reduction potential, the ability to undergo reduction. So the bigger the value, the easier for the species to undergo reduction. Okay, meaning if I compare an I2 plus with Ag plus, which one will undergo reduction better? It will be silver. Okay, so in other words, since it is easier for Ag plus to undergo reduction, it will become a stronger oxidizing agent. Okay, again, please correct your arrow inside your notes. The one that I show you over here is the correct one. Okay, and then how about the reducing agent? So the reducing agent will be vice versa. Okay, so let me erase it over here so you can see. Okay, so for the reducing agent, okay, inside your note, please correct the arrow as well. The arrow should be upwards. Okay, the more negative or the smaller the value of the E naught, you will have a stronger reducing agent. It will be vice versa of the oxidizing agent. Okay, so what you need to remember, if the value is big, it's a strong oxidizing agent. If the value is small, it's a stronger reducing agent. Okay, so please remember that. And then again, correct your arrow according to what I have over here. Okay, but if let's say you are taking the value from the SRP table. Okay, so your SRP table, so if I can scribble over here. Okay, SRP table, you will have the most positive value. Okay, up here is the most positive value and down here is the most negative value. So you can put the arrow if you have printed out your standard reduction potential table. Okay, so going upwards over here on the left hand side, okay, you will have increase oxidizing agent strength. Meaning, if it is located, okay, up over here, okay, over here is a very strong oxidizing agent, and down here very weak oxidizing agent. Okay, and it will be vice versa. Okay, so okay, this is again your SRP table. Okay, so going downwards over here, okay, the one that you have, okay, this is increasing, reducing agent strength. Okay, we will take the species on the right hand side, okay, on the product side, and if you have a negative value over here, meaning, what does it mean? You will have a very strong reducing agent. But if it is up over here, you will have a very weak reducing agent. Okay, the last part of 3.1, we're going to look on spontaneous and non-spontaneous reactions. So I will go through this very quickly. So what are we going to look on spontaneous and non-spontaneous reactions? So I mentioned before, I did mention the word, the reaction is spontaneous. How do we know the reaction is spontaneous? Spontaneous here means the reaction can occur naturally. So if you set up your galvanic cell and then you leave it as it is, the reaction will occur. Okay, and then you will get a positive value reading on your voltmeter. That will show that your reaction is spontaneous. Okay, it can occur naturally without we put anything. Okay, without we introduce anything into the system. Okay, so if we have a spontaneous reaction, the value of the E naught cell will be more than 0. Okay, where do we get the value of E naught cell? Read from the voltmeter. So if you have a positive value, what does it mean? You have a spontaneous reaction. But if you have a reading of E naught cell lower than 0, you have a negative value. So what does it mean? The reaction is non-spontaneous. Okay, what happens if we have a non-spontaneous reaction? There is no electrical energy produced, no electron flow, no electricity produced. But if you have a spontaneous reaction, what does it mean? there is electron flow, meaning you will produce electricity. And the last one, if the cell reaction is at equilibrium, the value of the E naught cell will equals to 0. Okay, so for this one, the reading at the voltmeter will be 0, meaning there is no potential difference. In other words, okay, your half cell, both of your half cell is the same, copper and copper, with the same concentration. So there will be no difference. The system will be at equilibrium, which you will not do. Okay, the system will either be spontaneous or non-spontaneous. But if we do the experiment in the lab, we want to have a spontaneous reaction. So we will do the setup for us to get a positive value on the voltmeter. Okay, so that's on the experiment part. But for question purpose, I give you over here two different examples. Okay, so let's take a look at example. So example calculation on spontaneity of reaction. If you see the word spontaneity over here, what does it mean? The question wants to ask you, is this setup of galvanic cell will give us a spontaneous reaction or not? Let's take a look at example 1. Okay, predict whether the following reaction occurs spontaneously. Okay, so I have here 2 Ag solid plus Br2 to produce 2 Ag plus 2 Br minus. Okay, for this kind of question, okay, you don't have to determine the cathode and anode based on the E naught cell. The value given over here, the E naught half cell over here, is just for you to substitute inside the equation later. Okay, the oxidation and reduction or the anode or cathode is determined by the half cell over here. Okay, so what do I mean? Okay, so Ag to Ag plus, Br2 to Br minus. So Ag here is 0, here is positive 1, meaning you will have oxidation over here. Oxidation meaning it is at anode. And Br2 is reduction. Okay, meaning it will be at our cathode. Okay, so the value that you have over here, so label them. So your silver Ag, this will be your E naught anode. And for Br2, this will be your E naught cathode. Okay, so that's the use of the value given over here. Okay, because we want to know, does this setup, okay, does this reaction is spontaneous or not? How are you going to do that? Okay, by calculating using the E naught cell. Okay, so E naught cell equals to E naught cathode minus E naught anode. So substitute the value. So E naught cathode is this one, positive 1.07 minus E naught anode is this one, positive 0.80. So what will be the value of E naught cell, standard cell potential that we will have? Okay, so you will get 0.27 volt, positive 0.27 volt over here. Okay, so after you do the calculation, what you will do is make a conclusion statement. So since, okay, let me change to my pen over here. So since E naught cell is bigger than 0, what does it mean? Okay, so reaction is spontaneous. Okay, please make sure that you spell it correctly. Okay, so let me just do it for you. Okay, reaction. Please do not put SRXN. Only I can do that because I'm teaching you. Okay, but in exam you must spell it out. Reaction like this. So reaction is spontaneous. Okay, will there be any equation with a non-spontaneous reaction? Yes. So that's why I prepare for you the second example. Okay, example 2. Calculate the standard cell potential for the following reaction and determine its spontaneity. So, the same step that you will do, find which one is your anode and which one is your cathode. So, as you can see over here, copper 0, copper 2 plus, positive 2. Meaning, this is your oxidation process. So, oxidation process will occur at anode. Okay, straight away I will label. So, E naught copper over here is my E naught anode. So, automatically, our zinc over here will undergo reduction. And where does the reduction occur? Cathode. Okay, I hope by now you already remember that cathode reduction, anode oxidation. So, E naught zinc over here is our E naught cathode. So, same step that we did just now to find either this reaction, the one given to you over here, is this spontaneous or not? Okay, we will know by calculating the value. So, E naught cell equals to E naught anode, E naught cathode minus E naught anode. And again, just take whatever value is given to you over here. So, the E naught cathode is negative 0.76, this one, minus the E naught anode, this one. Okay, positive 0.34 volts. And the E naught cell value that you will have is negative 0.42 volt. So, as you can see over here, you get a negative value of E naught cell. So, what does this mean? So, if you get a negative value, so make a conclusion statement that since E naught cell is less than 0, so what does it mean? Reaction is non-spontaneous. Yes, so you will write down like this. Okay, so this is the question that you will get in exam. Now, how do you make this reaction spontaneous? Okay, easy. You just, since copper to copper 2 plus is oxidation, and zinc 2 plus and zinc here is a reduction process, it will give you a negative value. So, it's a non-spontaneous reaction. Reaction will not occur. Electron will not flow. How do we get electron to flow? By reversing the equation. Instead of oxidation for these two, okay, it will be copper 2 plus to produce copper solid. It will undergo reduction. And this one will undergo oxidation. Okay, switch the anode and cathode. Okay, then you will get a positive value. Okay, so that will be all for 3.1 galvanic cell, and that will be the end of this video. So thank you for listening attentively until the end, and then we will meet again on the next video on 3.2 Nernst equation. So with that, thank you.